Okay, thanks for the invitation and the introduction. Well, in theory, I will talk about two things. One is criticizing a lot of approaches to induction and uncertainty. And then in the second half, talk a little bit about universal Bayes and AGI and universal AI. But we all know there's a difference between theory and practice. So in practice, probably I only will talk about the first half. Okay? Because on Saturday, I will also give a tutorial, 3 hours, and I will cover in detail universal induction and universal AI, and so I don't have to talk about that twice anyway. Okay, so the contents is first, I will argue a little bit why we need a general theory. It's not so important here to convince you because, I mean, we are all here wanting to build AGI, and the word G means general, right? Then I will talk about several either limited or unsuitable approaches to handling induction or uncertainty, at least from a fundamental, theoretically sound perspective. I will also explain sort of that most of these other approaches, they have their role, but I will mostly criticize them. Then, and if I have time, I'll talk a little bit about universal induction and AGI, which sort of solves the induction and the uncertainty problem, and then a little bit of discussion. Okay, so why deal with uncertainty at all? Well, the problem is that our world is only partially observable. So if we could completely observe our world and the laws of physics were deterministic, then we wouldn't have to deal with uncertainty. Okay? But even if we had a Laplace deterministic universe, because we can only partially observe it, we have only partial knowledge, so we are uncertain about various aspects and we have to deal with them. And therefore the induction problem needs to be solved. Also, many physicists believe, and there's good evidence, that the world is actually truly stochastic. So even if we could observe the complete world, there's indeterminism in the physical laws, so we have to deal with noise, probabilities, and so on. Again. Okay. Second, uncertainty comes in degrees. You can have low, medium, or high, on an even finer scale uncertainty. So we really need some real numbers or a dense field to characterize probabilities. It's not enough to say true, false, and uncertain or something like that. That is too crude. In general, I mean, for specific purposes, it may be sufficient. Okay? And also, I mean, ultimately, we're interested in building intelligent agents, and agents do something. So we have to deal with uncertainty in such a way that it can lead to decisions and actions. Okay? I will give an example of a quite sound theory of dealing with uncertainty, but it lacks the latter part, so it doesn't lead to actions. At least there are some problems with it. Okay? So the conclusion is that uncertainty induction have to be dealt with in a quantitative and graded manner. I guess most of you agree to that anyway. Okay, so here are some examples. The classical thing is hypothesis testing or hypothesis identification, so does treatment X cure cancer, or do observations of white swans, confirm that all ravens are black. I mean, this sounds a little bit funny, but that's a big philosophical problem. And you can never be sure about any hypothesis which is not a tautology, so you have to assign some measure of uncertainty to it, or degree of belief. Okay? Model selection is very similar. If you have different models, like are planetary orbits circles or ellipses, classical historical problem, there's a close relation between them. Parameter estimation is if you want to sort of the continuous version, you have a coin which has a bias, and the bias is a real number. You don't know the bias, and you want to estimate that, or the eccentricity of Earth's orbit, for instance. So these are induction problem in the narrow sense that you have data and you want to form a general model. And here are some prediction problems where you can directly go from past data or go directly from past data to future data. For instance, you have IQ sequences 1, 4, 9, 16. What comes next? Okay. I mean, usually what you do is you first try to infer a model from your data. Oh, these are the square numbers, and then you apply the model and do predict that the next is 25. But you could do a predictive approach and skip the intermediate step. So both is possible. Then another popular mode is classification, spam email classification, for instance. But in a sense, this is also just a sequence prediction problem. So you have an email, and you classify it as spam or not spam. You have another email, it's classified, and so on. And now you have a new email, and you want to classify it. So what you have is a sequence of emails and classifications, and then you have a new email you want to classify it. It's just a sequence prediction problem on a very abstract level. And so the big question is a general, formal, complete, and consistent theory of induction and prediction. So that's one question, and then another question is, can this then be used for guiding us, building agents which really make decisions and act? And another question is, do we need such a unified theory? Okay. And there are several reasons why we need it. So first, finding new rules for every particular new problem is cumbersome. Well, maybe we have sort of fuzzy logic refers here, and then we have possibility refers here. So we have all these kinds of theories, and they have their application domain. And then we have a new problem, right? Yeah. And what do? We invent a new theory, and that's laborious. Yeah. So it would be great to have one theory which covers everything. Okay. And but even more important, or equally important, is that if you have a plurality of theories, they are prone to disagreement or contradiction. So you have two theories, and first you have to ask which theory you can apply in which context. Then if you have an overlapping domain of application, it's even more severe, so which theory gives you the better answer. So what you then really need if you want to build an AGI system, you need a meta theory which tells you which theory of uncertainty or induction to use. And then you can argue, well, if I have this meta theory plus the underlying theories, this overall is one theory. I mean, this is a matter of language and perspective, and I wouldn't mind too much if we had this meta theory, but we don't have it. Okay? And then by analogy to other fields, I mean, especially I have a whole slide on that, deduction. Yeah, we have in a sense, unique basis for doing logic and mathematics, right? You start with, in principle, Zermelo-Fraenkel set theory, and you can build whole of mathematics out of that. Okay? And that really boosted the field of mathematics to very high levels. And we need something similar for induction and AGI. Okay? There's also a problem, say, the classical one are the frequentists and the Bayesians, you know? Okay? So now you have a customer, and you know, he goes to the frequentist, and he tells him, do this, and then you have a Bayesian and tells him, do this, yeah? And he says, I don't care, just give me the best answer, you know, I don't care about all these differences, right? Yeah. So then again, we would either need a meta theory, which tells me which is best in which situation, or we need a unified theory, or just scrap everything and, you know, have one theory which just works, okay? And also, I mean, many of these existing practical or heuristic or maybe limited approaches are still, of course, very useful. But having such a unified theory helps us to show the limitations of the existing theories, maybe define better the domain of applicability, and so on. Okay? And also, it is necessary for resolving philosophical problems if you're inclined to sort of like these problems. I mean, as long as you have two theories which give different answers, you have a philosophical problem, right? And while finally, you know, often unified theories are very good. So, and there's no convincing argument that the goal is not attainable. I will talk about some of the arguments against it, like no free lunch or so, and why they don't bite. Okay, so here now comes, and I want to spend quite some time on that, a list of either unsuitable or limited approaches to dealing with either uncertainty or induction or both. And this will be, I have to go rather quickly through all these approaches, although I could spend, or would like to spend 3 hours on that. Okay, first, maybe my all-time favorite is Popper's approach to induction, which is seriously flawed. Okay, first, I mean, these are sort of 3 main statements he does, and it's really, some parts are a caricature. I have to be really very brief about that. So, first, the falsification is too limited. So, I mean, that's the proposal here, that so theories need to be falsifiable, but I mean, the famous example is all emeralds are green, and then you have all emeralds till the year 2020 are green, and then suddenly they are blue. Both theories are completely consistent with our observations, and not, I mean, they're both falsifiable, but not falsified yet, yeah, so Popper, at least this line cannot tell us which theory is better, although one is obviously absurd. Although we have to be careful what does it mean, obvious and absurd, okay? Then he says confirmation of theories is not possible, but if you look more carefully into it, and also simplifying, either his suggestion of using corroboration is exactly the same as confirmation, or it's meaningless. You pick, okay? And finally then, I mean, he realized that he needs some bias towards simplicity, like with these two hypotheses, where one was obviously absurd. But he says he identified simplicity with easy to refute. Coming back to the falsification dogma, but which also doesn't work. It's easy counterexample. Okay, that's enough about Popper. So Popper is essentially dead. Okay. So no free lunch myth. Most of you have heard about that, and the no free lunch theorem mostly, and it's quite famous in some communities. It's you have to start a paper or a talk by, look, there's a no free lunch theorem. That's the reason why we cannot have universal systems, but we have to build a very specific one which just solves my problem. Right? Okay. So you hear that quite a lot. But while the theorem, the no free lunch theorem, is correct, its use and interpretation is wrong or is misused. Okay, the no free lunch theorem says that if I have a uniform distribution over my space of functions, then any optimization algorithm is as good as any other. Okay, this result is true, but completely useless, because a uniform distribution over function space is not uninformative, as it often claims. It actually has a very strong bias, namely a strong bias towards total random noise. Yeah? So uniform distribution over function space means that with probability 1 or close to 1, your function is white noise. And well, first we know we cannot be smart on white noise, and second, we don't care. I mean, very few people care about watching on a noisy screen and trying to sort of find the brightest pixel or so, right? Yeah. So this theorem doesn't really bite. Okay? So then we have frequentism. Several problems. The interpretation, the definition is circular. No time to go into that. It's essentially limited to independent, identically distributed data. And then there's the reference class problem. So there are lots of problems with frequentism, or I mean, the simplest form of frequentism. But people have extended that. I mean, statistical learning theory is, to a large degree, sort of frequentist. I mean, there's also Bayesian in there. But the essential assumption of IID is still there. The reference class problem, by complexity penalties, goes away a little bit. And with the circular definitions, there's Kono's principle, you can get away with it. But essentially, most of statistical learning theory is limited to IID data. And, you know, the real world is not Las Vegas, right? Where you go there, play once, and you play another time, and everything is independent. The real world is much more complicated. You drive a car, you make one error, you're either dead or, you know, you're, whatever can happen, yeah? Or you fail your final test in university, you can never repeat it. So the world is, I mean, not even ergodic or any of these nice worlds which theorists often assume. Okay. So, but I have more. So let's go on. So what is this subjective Bayesianism? Okay, subjective Bayesianism says you have to have a subjective prior belief which you somehow elicit. Okay. So the problem is there's no formal procedure of getting your prior. And if we want to build AGI, we need a formal procedure. Okay. So then let's go to objective Bayes. Objective Bayes say, if you don't know anything, there are objective rules based on some principles which give us uninformative prior. I mean, the standard one is Jeffrey's prior, for instance. That is right in spirit, but too limited for AGI. It essentially works for finite and for compact classes, and the world is not compact. Okay, but it's right in spirit, but you have to do a little bit harder, a little bit more. Okay, MDL, MML is pretty good, and I personally regard it as practical approximations of Bayesian theory. Okay. So while I talked about pluralism, this is fashionable nowadays. Okay, let's be pluralistic, open-minded, and so on. This is fine, but if you want to build a single AGI system which is able to drive a car and play chess, you know, we either need a single theory or we need a meta theory which combines our specific theories. Yeah? And so pluralism is, as it stands globally, inconsistent and not sufficient. Then deductive logic. Okay, deductive logic is great, but of course we can't do induction with it, which we need to do. But people have tried to extend that, for instance, non-monotonic reasoning, inductive logic, default reasoning, probably many, many more. But they all don't take uncertainty properly into account. I mean, in the most limited forms, you just have true, false, and I don't know, and you know, they have been extended, but they don't take uncertainty into account sufficiently well. So from a more philosophical camp, there's Carnap's confirmation theory, which is closely related to Bayes and Laplace rule, which is, in a sense, pretty good. I mean, it was from the 40s or so. It was a long time ago, so not bad for these times. It was even before Solomonoff. But it's also limited to exchangeable data. It's more or less mixtures of ID data, and the world is not like that. But the real problem is that it can't confirm universal hypothesis. So if you ask, for instance, the hypothesis, whenever it rains, the street is wet. This theory can't confirm it, even if you have observed it 100,000 times. You know, the classic philosophical examples, all ravens are black. These hypotheses cannot be confirmed with Carnap's confirmation theory, which is a big problem. And maybe you ask, okay, I don't care about black ravens and all these problems, I care about real problems, but these toy philosophical problems will appear in your real problems, somehow deeply inside. And if you're lucky, it's not too important and you get away with it, but if you build an AGI, it will fail on some real-world problem which has sort of these problems somewhere deep inside. Okay, then we have sort of the big data theme, which is also very fashionable. We have big data, so we don't have to do much smart things. We just crunch through them with some primitive algorithms and all our problems are solved. And you get actually quite far with that. But my claim is you don't get AGI with that. So, I mean, the big data paradigm and crunching through the data in a simplistic way is more than lookup table. But it has the tendency of being sort of closer to the lookup table approach, and lookup table AGI will not work. Okay. There's sort of the good old Goldstein eliminative induction, which is a nice theory, but again it ignores uncertainty. Right? You just eliminate the hypotheses which are inconsistent with your data, and you pick the next one, which is the first one, which is not inconsistent. And then, I mean, I just pick there's so many, I can't list them all, and I don't know them all, and I don't know much about them, but let's say pick one, like fuzzy logic or fuzzy sets. I mean, depending how you view them, either the foundations are not sound, or they are heuristic, or they're too limited. It depends a little bit where you come from. Okay. Imprecise probabilities is, in a sense, quite interesting because it extends classical Bayesian inference by, instead of taking a single prior, you take a set of priors, because we don't know well where these priors come from. So just like take the set of priors where hopefully the true prior, whatever that is in this set. Yeah? It's sort of a conservative, robust, but it's a little bit different from robust Bayes approach. The problem here is if you start with a set of priors, you get a set of posteriors, and then you get a set of decisions. That's fine for some purposes. Say you have medical doctors, and one does this, and the other one does that, and you ask, is one better than the other, or does one do something very bad? Yeah. If you use this theory, you come up with a set of solutions, say, whenever you're in this set, you're fine. Yeah? But if you want to build an agent, he has to act somehow. He has to choose one action. And if you get a set of actions, what shall you do, right? If you pick an arbitrary one, then you undermine the whole point of imprecise probability. You could have started with an arbitrary probability distribution among this set. Okay. I think that should be enough about other approaches. So they all have their faults. And of course, I mean, it is easy to criticize approaches, but the question is there something out which is better? Okay. And also, I mean, all these approaches I've criticized, they have their domain of application, so they have their use. Okay, but I don't think they will ever be able to serve as a foundation of AGI. So let me spend the remaining 8 minutes or so on what now? So first, there seems to be quite little controversy outside of logic that the logic we have now, say first order logic or higher order, doesn't really matter. We take similar Frankel axioms, we build whole of mathematics out of it, everything is fine and nice. Yes, we have to do the incompleteness theorem, but we have to live with it. Yeah. So, I mean, there is no argument if you look at Fermat's last theorem with the proof or whatever, you know, oh, have you chosen the right logic or not? You know, these arguments are within logic and people trying to improve that, but outside of logic, we use a standard logic, say, and we all agree on what is a proof or not. So deduction in this sense is solved, okay? So induction is often claimed to be in a much worse state, and my claim is that is not true. Induction is nearly in as good state as deduction. So I made this table here to compare deduction to induction. So deduction does sort of specializes from general theorems or derives things with rigor. I mean, provably true, while induction generalizes from specific data, so it's in a sense complementary. The general framework in deduction is logical axioms, while in induction, okay, my claim is Kolmogorov axioms of probability. Okay. Then what are the assumptions? The assumptions in mathematics are the non-logical axioms like piano arithmetic, while in induction it's the prior. Okay. You cannot prove that the piano axioms are the right ones. You can't just start with and show that they have consequences which conform to reality. So if I take one apple and one apple, it's two apples. But if I take one cloud and one cloud, it doesn't necessarily give two clouds. So it breaks down for clouds, so you cannot apply to that. But there's a big area of application. Okay, so you choose non-logical axioms and apply it to some domains. And here, in induction, you choose priors. Okay, how do you do inference? In the most simple thing, systems like Hilbert's calculus, you only need modus ponens. So if A is true and A implies B, then B is true. And that's all you need. And in induction, the only thing you need is base rule. Okay. What are the results? Well, in mathematics, in deduction, it's theorems, while in induction, it's the posterior. So now we can ask, is there a universal scheme which is able to cover everything? And in deduction, it's similar Frankel set theory. I mean, you could start with equivalent systems. I'm fine with that. And in induction, it's Solomonoff's probability distribution. And we'll talk about that in the tutorial on Saturday in detail. Okay, so what are the limitations? Okay, in deduction, we have Gödel's incompleteness theorem. So, I mean, there are true statements which cannot be proven, but we somehow live with it, and you can't do much about it. Okay. Well, in induction, we also have limitations, and the corresponding thing is the incomputability. I mean, this is a true statement which you can't prove, and proofs are the analogon of computations, right? And this is an incomputable theory. But just as we have learned to deal with true but unprovable statements, we will be able to learn to deal with incomputability by building computable approximations, which then have limitations and so on. I mean, automatic theory improvers are very, very limited, yeah? But that doesn't undermine the underlying powerful theory. And then, what do we do in practice? Well, we use semi-formal proofs, right? I mean, very few proofs are written down in set of C. I mean, they're horrible to read, except for computers. And here in practice, we do some approximations in induction. Okay, and the basic mode of operation in deduction is proof, and in induction, it's computation, computing the posterior in a sense. Okay, so there's a nice analogy. I mean, I know it's not perfect, but it's better than most people believe. Okay, and well, I have to fill this in, of course. I mean, basis there, posterior, prior, that's all rigorous and all known. But well, Solomonoff, hopefully you've heard about it, but maybe you don't know the details. And on Saturday I will talk about the details of this one. Okay, so my claim is that the foundations of inductions are as solid or nearly as solid as those of deduction. And the foundations are based on Epicurus' principle, Occam's simplicity principle. I don't have to explain that. But we also need Epicurus' principle of multiple explanations, which is sort of complementary to Occam. Occam says keep the simplest theory. Epicurus says keep all theories. It sounds like a problem, but we can marry them both very easily. We just keep all of them, but have a bias towards simplicity. And now we need to formalize that. And well, we use Bayes' rule for updating beliefs. And but how do we get the prior? Well, we need to quantify simplicity Well, first we need the concept of a Turing machine, interestingly not for computing purposes, but for defining what complexity or simplicity means via Kolmogorov complexity. And then Solomonoff in the 60s already put everything together into one universal theory of induction, which is essentially base plus a prior, which is 2 to the minus the Kolmogorov complexity of your hypothesis. Okay? And well, in some sense, the only thing which I added was the theory of sequential decision making, Sense-Bellman equations, which then leads from an induction prediction system to a system which really makes decisions and acts. And here are some properties of universal induction. And now Laurent has to tell me how much time he is willing to give me for more.
5 minutes.
Okay, so the theory of universal induction, I just put this there without sort of arguing for it. You have to wait for Saturday. So it's formal, complete, general, and globally consistent. Has lots of optimality, proves optimal error bounds. Essentially, you can say whatever prediction system you use, Solomonoff will not be worse and often better. Okay. If no prediction system works, like maybe predicting the stock market, maybe that's in principle impossible, then of course Solomonoff will also fail. Okay? But if something works, Solomonoff will also work. So that's sort of the gist of the theorems. It solves the zero prior problem. That's a philosophical problem. It can confirm universal hypothesis. Like I've mentioned, if it rains, then the street is wet, or all ravens are black. Some statistical important property is its reparameterization and regrouping invariant. Solves the problem of evidence and updating. These are major problems which have been discussed mostly in philosophy about many induction systems. It also allows to incorporate prior knowledge. I mean, as it stands, it does not use prior knowledge, but it's easy to include it. And it can be integrated into rational decision agents. Of course, everything has downsides, and here are some downsides. If you have a small toy problem, like I see 10 ones, what is the next bit? There are some problems, which is theory, but there are also ways to overcome it. Okay, so prediction in toy problems or short problems are problematic as it stands. Then in all these results you have constant additive fudges, and you have this universal Turing machine dependence, which is annoying. There's sort of, in practice you can live with this situation, but it would be much nicer if there were a theoretical solution. And well, the biggest problem is that it's incomputable, and you can show that every practical approximation must be, on some problems, very crude. Okay. So, okay, and now you can plug that into decision making and come to actions. I will skip that, and you get the universal AGI model. So you get this equation here, which looks a little bit complicated, but given that, at least this is my claim, and I have proofs of that, that this is the most intelligent agent possible, it is quite amazingly short. I mean, everything is explicit here except for the concept of a universal Turing machine. Sort of, this is not explicitly defined. Okay, you have to wait for Saturday, and then I explain that. Okay, so fine, so good. Nice theory, you can prove that this solves the problem, but ultimately even I want to build a system which works in practice. Okay, what do? We approximate the theory, and already with dealing with Bayesian probabilities is often intractable. So we need approximations, but you should approximate the solution and not the problem, right? It is good to know this is the principal optimal solution, and now we approximate the solution. If you approximate the problem already, your system will always stay limited. I will come to that in the last bullet item, and maybe then I'll stop. So what I claim is that whatever heuristic method or limited method you use, ultimately you should compare to the gold standard Solomonoff and AGI and see what is missing and how could I incorporate that. Right? I have nothing against bottom-up approaches, but I mean we all want to reach the same goal, right? Generically, and you can go top-down like I, or can go bottom-up, but we have to sort of meet somewhere in the middle. And I mean, if you have a too cheap surrogate, it will just fail in critical situations, and then what? Okay. Well, there are some quite generic approximations which are quite like, which have potentially the power of scaling up to AGI. What you have to do is, if you design your own theory or algorithm or so, try to build it in such a way that it's scaling up by itself to an AGI, or phrased differently, that you want an anytime algorithm. So if you have an agent who thinks a second about a problem, it should come up with some solution. If it thinks a minute about the problem, it comes up with a better solution. If it thinks a year, it comes up with an even better solution. If you have a system which just gives you after 1 minute an answer and that's it, then for sure your system will stay limited. Well, if you just play tic-tac-toe, well, I don't need a minute, yeah, or a year, right, yeah, to play optimal tic-tac-toe. But if I have a real-world problem, I mean, even playing chess, yeah, or but driving a car, or say designing a space rocket or something like that. If I think a second, the rocket will be worse than if I think a minute or a year, and so on. Yeah. So we need anytime algorithms, and well, an anytime algorithm, if you give it arbitrarily much computation time, the question is, what answer should it give you? What is sort of the asymptotics? And the answer should be then AGI or Solomonoff, right? If it falls below, your system will fail where some other system could succeed. Okay, and then it's not really machine superintelligence anymore. So I have more. This is just a summary. So I leave it for a second for the camera. Then some advice to philosophers and AGI researchers, which I just told you. And here's one of my favorite lines. Yeah, I mean, if you're more practically inclined and you have the attitude that you should not trust a theory if it's not supported by experiment, I'm with you. There are lots of theory which is pretty useless, but the reverse is equally true. You should not trust an experiment if it's not supported by a theory, right? Yeah. You can hack all kinds of things and then, well, it works in this domain, and then you hope that it works there, but usually it doesn't if there is no theory behind it. Okay, there are cases where you can ignore all this theory, essentially if your system already works well enough for your purpose. I talked a little about information theory, which plays a central part in universal induction, some outlook, and I think I'll stop here for the next speaker, not for questions, or except technical questions, I guess.